Welcome back to AI Paper Podcasts. Today, we're digging into a paper that fundamentally changes how we think about agent orchestration. It's called SkillOrchestra Learning to Route Agents via Skill Transfer, and it comes out of UW-Madison and Salesforce AI Research.
And this is a massive paper for anyone building compound AI systems. It directly tackles the elephant in the room, which is routing collapse. Current reinforcement learning-based routers are just, well, they're failing. They get lazy during training and default to the most expensive model, usually something like a Llama 370B class model, about 90% of the time.
Which completely defeats the entire purpose of having a router in the first place.
Exactly.
So the solution proposed here, SkillOrchestra, it abandons end-to-end policy learning entirely. Instead, it learns what they call a Skill Handbook by analyzing execution traces to figure out exactly which fine-grained skills are actually needed for a given task.
And the performance jump is significant. SkillOrchestra outperforms state-of-the-art RL orchestrator systems like Router R1 and Tool Orchestra by up to 22.5% in accuracy.
While being dramatically cheaper to train, we were talking a 700x reduction in learning costs compared to Router R1.
Plus, and this is the real killer feature here, transferability. You can learn this handbook on a tiny model and transfer to a completely different orchestrator backbone without any retraining. It's a huge step forward for modular AI.
So let's get into the weeds here. We hear the term compound AI systems thrown around a lot lately.
Yeah, everywhere.
But we aren't just talking about a simple RAG pipeline where you query a database and summarize it.
No, not at all. We're talking about complex agentic workflows. Think of systems like Gemini Deep Research or the new wave of scientific discovery agents. These systems have access to a whole tool belt, Python interpreters, web search, calculators, and crucially, they have a model pool.
Right. You don't just have one LLM doing everything. You have a roster of them.
Exactly. You have your heavy lifters, your PhD consultants, let's say, like GPT-4 or Claude Opus. They are brilliant, but they are slow and very expensive. Yeah. Then you have the interns. Models like Mistral 7B or Llama 8B. They're fast, they're incredibly cheap, but if you give them a complex logic puzzle, they might just hallucinate and break down.
And the economic imperative here is obvious for anyone deploying these. If you are building an enterprise agent, you cannot afford to pay the PhD consultant rate for every single subtask.
Right.
Especially if the task is just, formatting a date string or fetching a basic URL.
Precisely. That is just burning GPU credits for no reason. You want to route that simple query to the intern. But the problem is, figuring out when it's safe to use the intern is actually incredibly difficult in the middle of a dynamic, multi-step conversation.
So historically, how have people tried to solve this? Because the paper mentions input-level routers first.
Yeah, input-level routing is kind of the naive approach. It just classifies the user's initial prompt right out of the gate. It sees the prompt and says, oh, this looks like a math question. Let's write it to the math model.
Which sounds fine in theory.
Sure, but in a multi-step workflow, the requirements constantly shift. You might start with a math question, but then step 2 requires a web search to find a constant, and step 3 requires summarizing text. A static decision made at the very start just fails to capture any of that nuance.
So then the industry naturally moved to RL-based orchestration.
Right, which is the current standard.
Right.
You train a manager agent using reinforcement learning. You reward it when it picks a cheap model that gets the right answer, and you punish it when it fails. In theory, it should learn this perfect, elegant balance.
But in practice, we get this routing collapse phenomenon. Why exactly does that happen? Because intuitively, RL should figure this out.
It's a classic exploitation failure. Imagine you're that manager agent. You try sending a task to the cheap model, Mistral, it fails. You get a negative reward.
Ouch.
Right. So next time you send it to the massive, expensive model, Llama 70B, it succeeds. You get a positive reward.
So the lesson the neural net learns is basically big model equals safe.
Exactly. The RL agent becomes extremely risk-averse. It realizes that exploring the capabilities of the smaller models is actually dangerous to its reward function. So it just converges to this local optimum where it spams the biggest model available.
It's just gaming the metric.
Totally. The paper actually cites data on Router R1 showing it routed 98% of its calls to Llama 3.170.
That's insane. So you spent all that time and all that compute training in advanced RL router only for it to act like a simple pass-through script to the most expensive API.
Yep. It's incredibly inefficient and totally unscalable. And that is exactly where Skill Orchestra flits the whole paradigm. The authors essentially say, stop trying to learn a black box routing policy via trial and error. Let's explicitly model what these agents can actually do.
And this leads us to the Skill Handbook, which is a great name, by the way. And this isn't just a metaphor they use, it's an actual concrete data structure in the system.
It is. It's a structured database, and it's built on 3 specific layers. The top layer is mode selection insights.
Which is what exactly?
That's the high-level strategy. Is the current state of the workflow requiring a web search or Python coding or just conversational chat?
Okay, so a broad categorization first.
Right. Then you drop down a level to fine-grained skills. And this is critical. They don't just label a task as coding and call it a day. They break it down heavily. Is it high-precision arithmetic? Is it symbolic logic? Is it data visualization?
Because that distinction really matters. A smaller model might be an absolute wizard at basic arithmetic, but terrible at symbolic logic.
Exactly.
And if you just lump both of those under the umbrella of coding, the router can't tell the difference and will probably default to the expensive model just to be safe.
Exactly right. And then the third layer at the very bottom is the agent profiles. This is the actual statistical record. For every single agent, which they define as a specific model plus a specific tool, the handbook tracks their performance on those specific fine-grained skills.
So it's literally a lookup table. It says Mistral 7B is 95% effective at arithmetic, but only 20% effective at logic.
Yeah. And the beauty of this is it makes the routing interpretable. In an RL system, if it picks a model, you have no idea why. But here, you can check the handbook and see, oh, we picked Mistral for this step because it has the highest success probability for this specific skill at the lowest computational cost.
Now, for the technical folks listening, I think the obvious red flag or question here is the scalability of getting all that metadata. You can't just have humans manually labeling symbolic logic on millions of interaction traces.
No, that would take years.
So how does Skill Orchestra actually build this handbook automatically?
So this is what they call the learning phase. And it uses a really clever technique called trace analysis, combined with an LLM that they call the discoverer.
Trace analysis. How does that process work under the hood?
The system takes a user query, and it looks at 2 different execution trajectories. One where an agent succeeded the positive trace, and one where it failed the negative trace.
Okay.
Then it computes the difference between them, which mathematically they denote as DDIF.
So it's literally isolating the delta in the execution path, looking at where they diverged.
Right. And then it feeds that difference, that DDIF, into a powerful LLM, the discoverer. And it effectively asks the discoverer what specific capability was missing in the negative trajectory that was present or required for the positive one to succeed.
Wow. So it automates the root cause analysis.
Exactly. The discoverer might analyze the trace and say, the failure happened because the model couldn't handle relational constraint satisfaction.
Boom.
Boom. The system takes that and registers relational constraint satisfaction as a brand new fine-grained skill in the handbook.
That is elegant. But once a skill is discovered and added to the handbook, how do they track the performance? Because the paper emphasizes they don't just use a simple average win rate, they use beta distributions. Why go that deep into the math?
Well, it's absolutely crucial for handling uncertainty. Let's say an agent tries a brand new skill for the very first time and it succeeds.
Okay.
If you use a simple average, it has a 100% success rate.
Which is true, technically.
True. But a sample size of 1 is statistically meaningless. You do not want your router betting the entire workflow on a sample size of 1. 1 for 1 is not the same as 1,000 for 1,000.
Right. The confidence isn't there.
Exactly. So by using beta distributions, they model the success probability as a distribution curve, not just a single static number. The distribution relies on 2 parameters, alpha, which represents successes, and beta, which represents failures.
So when you have very little data, what does that curve look like?
When data is sparse, the distribution is wide and flat. The system mathematically knows it is uncertain. But as the agent performs that skill more and more, you update those alpha and beta parameters.
And the curve tightens up.
It peaks right around the true mean.
So the router can actually make decisions based on confidence intervals rather than just raw, potentially misleading averages.
Precisely. And that allows the system to balance exploration and exploitation mathematically. It intrinsically knows when it needs more data to verify a model's competence on a skill without needing this massive, complex RL training loop to figure it out.
But wait, doesn't this list of skills eventually just get incredibly messy? I can easily imagine an LLM discoverer coming up with 50 slightly different ways to say math over thousands of traces.
Yes, and they accounted for that.
Yep.
That brings us to the refinement phase. They use another LLM called the Reflector to basically act as a strict editor for the handbook. It performs two main operations, splitting and merging.
Splitting is for when a skill is defined too broadly.
Right. Let's say the handbook has a skill just called reasoning. But when you look at the beta distributions, a specific agent's performance on reasoning has incredibly high variance. It succeeds wildly sometimes and fails miserably others.
Which means the label is probably useless.
Exactly. The reflector looks at that variance and realizes reasoning is too vague. So it splits it into, say, deductive reasoning and inductive reasoning to get a much cleaner, more reliable statistical signal.
That makes sense. And merging is just the reverse.
Pretty much. If you have arithmetic and calculation as two separate skills, but the reflector sees that they have statistically identical performance profiles across all the agents in the pool.
It just merges them to remove the redundancy.
Right. It keeps the handbook lean and efficient.
Okay, so we've built this incredibly detailed, mathematically sound handbook offline. Now we are at inference time. A live user sends a query. How does the system actually use this data without lagging out?
This brings us to what they call Pareto optimal handbook selection. Yes, remember, you can't fit the entire historical database of every skill ever learned into the context window of the router. It's way too many tokens. It would be expensive and slow.
So it needs like a Cliff Notes version for this specific query.
Exactly. The system dynamically selects a subset of skills and profiles that lie on the Pareto frontier.
Meaning it's balancing trade-off.
Right. It balances expressiveness, which is having enough diverse skills to actually cover whatever the user might ask, with decision reliability. It picks the most statistically informative, compact subset of the handbook for the current deployment constraints.
And I assume this architecture is exactly what enables that transferability breakthrough we teased at the beginning.
Oh, absolutely. And this is arguably the most important contribution in the paper for the ML engineers out there listening. In the old RL paradigm, the knowledge of how to route is literally baked into the neural network weights of the router itself.
So if you want to upgrade your router from Llama 2 to Llama 3,
You have to throw away the old router and retrain the new one from scratch.
which is a massive, expensive pain.
Totally.
Yeah.
But with Skill Orchestra, the knowledge isn't in the weights. The knowledge is in the handbook. It's an external readable data set. The paper actually demonstrates that they could run the learning phase using a small model like Qwen 2.53b as the orchestrator.
A tiny...
Right. And it builds a great handbook. Then they take that exact same handbook and just hand it over to a completely different, larger model to act as the runtime orchestrator.
Without any retraining.
Zero retraining. And it still achieves massive performance gains.
You are fundamentally decoupling the manager's innate intelligence from the actual knowledge of the team's capabilities.
Perfectly put. You can fire the old manager, hire a new one, hand them the team dossier, and they can start routing tasks perfectly on day one. This completely solves the cold start problem for deploying new agents.
That is brilliant. Let's get into some of the hard results. They tested this against 10 different benchmarks, right? Things like math and hotpot QA. What do the actual numbers look like?
Figure 1 in the paper really tells the whole story visually. You have accuracy on the y-axis and cost on the x-axis. Skill Orchestra sits right up there in the top left corner.
High accuracy, low cost.
Yeah.
The holy grail. Let's look at the math benchmark specifically, because that's usually the absolute torture test for AI reasoning.
Yeah, math is brutal. On the math benchmark, the reinforcement learning baseline, Router R1, achieved about 55.8% accuracy.
Okay.
Skill Orchestra hit 73.6%.
Wow. That is a massive delta. That's nearly an 18 percentage point jump on a notoriously hard benchmark.
It is huge. And it gets better when you look at the cost.
Right, because accuracy is great, but not if it bankrupts you.
Exactly. Router R1 cost roughly 6.5 cents per query on that benchmark. Skill Orchestra dropped that down to 3.6 cents.
So you are getting significantly higher accuracy for almost half the price per query.
Yes. And this loops right back to that routing collapse visualization I mentioned earlier, which is figure 6 in the paper.
The pie charts.
The pie charts, yeah. If you look at the Router R1 utilization chart, it's just a solid blue circle. It's 98% Llama 7DB. It's a complete monopoly. The router learned nothing except to use the biggest model. But then you look at the Skill Orchestra chart, and it's this beautiful multicolored pie. You see about 44% usage of Mistral 7B, 26% usage of Quen, and only a relatively small slice for the massive, expensive models.
It actually proves that the small models can do the heavy lifting if they're just routed correctly.
It proves the interns are highly capable if the manager actually knows which specific tasks to assign them. The RLer didn't know their skills, so it didn't trust them. The handbook knows definitively that Mistral is 100% capable of, say, attribute retrieval. So it routes that task there with total mathematical confidence.
There's also a really interesting qualitative difference in how the model actually behaves at runtime. The paper highlights the use of think tags in the logs.
Yes, this is very chain of thought. Before the orchestrator routes a query, it actually explicitly reasons out loud about its decision.
Right in the output.
Yeah. It outputs a thought process. Like, to answer this user query, I need external information. The specific skill required is attribute retrieval. Let me check the handbook. According to the handbook, Mistral 7B has a high success rate and tight confidence interval for this skill. So I will route to Mistral.
That is so huge for debugging. I mean, in a typical RL setup, if the router screws up and sends a math problem to a language-only model, it's a black box. You have absolutely no idea why it picked the wrong model.
Exactly. You just stare at the weights. But here, you can literally read the think block. You might see, oh, it thought the required skill was X, but based on the prompt, it was actually Y.
It makes the entire orchestration layer transparent and debuggable.
Which is what enterprise users are begging for.
I want to walk through one of the specific examples from the paper just to make this super concrete for you listening. There's a query where a user asks who was the composer of It's Gonna Take Some Time.
Oh yeah, that is a great example of dynamic multi-turn routing. In turn 1, the orchestrator checks the handbook and sees that Quen 2.57b is very cheap and usually quite good at basic retrieval. So it routes the initial query to Quen.
But Quen fails. If you read the transcript, it basically glitches out and just repeats, let me know your next step, without actually answering the prompt.
It completely drops the ball. So the orchestrator sees the failure. And in turn 2, inside those think tags, it explicitly reasons. It says, Quen failed to provide a definitive answer. I need a model with stronger factual knowledge for this specific entity.
It escalates the ticket.
It totally does. It checks the profiles again and decides to route the query to Llama 3.17db.
The big guns.
But interestingly, even Llama 7db is a little unsure. It gives an answer, but it hedges its language.
Right, it's not perfectly confident.
So the orchestrator catches that uncertainty and triggers a turn 3, which it classifies as cross-verification. It brings in a third model entirely just to verify the findings of the second model.
That's wild. It's not just blindly firing off API calls based on the first prompt. It is actively reacting to the quality of the output it receives, step by step.
And that is exactly why they call it the orchestra. It's actively conducting the agents based on how they are actually performing in real time.
Another really interesting component of the handbook is the mode selection insights layer at the top. We touched on this briefly, but it seems like it also captures best practices, not just raw model stats.
It absolutely does. The system learns actual heuristics from the traces. For example, the paper notes it learns strategies like search.efficiency.tool call minimization.
Which means what in plain English?
Basically, the system learned, do not write a complex Python script to scrape a website if a simple DuckDuckGo search query will suffice.
So it's effectively writing its own best practices manual for using its tools efficiently.
Correct. And because it's constantly learned from data, it adapts. If a new, highly efficient search tool gets added to the pool, the handbook will eventually update to reflect that using that new tool is the new best practice for that skill.
Okay, I do want to circle back to the Discover LLM for a second. We mentioned it uses a really strong model like GPT-4 to analyze the traces and find these skills.
Yeah.
Doesn't that get insanely expensive? Having GPT-4 read thousands of logs just to build a handbook.
That is a very valid concern, but you really have to distinguish between training cost and inference cost here.
Okay.
Yes, building the handbook burns compute because you are using a frontier model to analyze all those traces. But you do that once. It's an offline process.
So it's basically CapEx versus OpEx.
Exactly. You pay the compute tax up front as a one-time capital expense to build the handbook. Then, at runtime, when you are actually serving millions of live user queries, which is your operational expense, you save massive amounts of money because you can safely use the cheap interns 80% of the time.
And even with that upfront GPT-4 cost, the paper claims this whole learning process is still cheaper than the reinforcement learning alternative.
Much, much cheaper. RL requires thousands upon thousands of iterative loops to finally converge on a somewhat decent policy. The Skill Orchestra approach is incredibly data efficient.
Because it's explicitly extracting the reason for failure rather than just guessing.
Right. You don't need a million traces to figure out that Mistral is good at basic math. A few hundred labeled examples in the handbook give you a very strong, statistically significant signal via those beta distributions. And that is exactly where that 700x cheaper metric comes from.
It's just a much smarter use of data. As we look toward the future of this research, the scalability aspect seems to be the most critical takeaway. We are seeing new, highly specialized models drop every single week now. Audio models, vision models, specialized biology models.
And if you stick with the RL routing paradigm, you have a massive bottleneck. Every single time you add a new biology agent to your pool, you basically have to retrain your entire router so it learns about the new agent's quirks. It's slow and prohibitive.
But with Skill Orchestra,
it's completely modular. You add the biology agent to the pool, you run a small batch of test traces. The discoverer analyzes them, identifies its unique skills like protein folding or sequence analysis, and just appends them to the handbook.
you don't retrain the router's brain at all.
No, you just update its contact list.
It really changes the metaphor from training a monolithic neural network to just updating a dynamic database.
Which is honestly the only practical way we are ever going to manage pools of hundreds or even thousands of specialized agents in the future.
It brings up a really provocative thought to end on. If we can map AI capabilities to a skill handbook this effectively, breaking them down into fine-grained skills and confidence intervals, are we basically seeing the birth of a standardized resume for AI agents?
Oh, that is a really fascinating way to frame it. I mean, currently, we rely on these generic benchmarks, right, like MMLU.
Right, which is just a single, highly gameable number.
Exactly. But with this, we might start looking at an agent's handbook profile instead.
Hi, I'm Mistral 7B. My profile shows I am a senior specialist in high-precision arithmetic, but I'm basically a junior intern in creative writing.
Exactly that. Imagine a system that says, please submit your Skill Orchestra profile before applying to handle this subquery.
Wow.
It could standardize how we evaluate, trade, and deploy these models entirely across different platforms. It turns vague capability into a strictly queryable data format.
A standardized resume for the synthetic workforce, it makes a ton of sense.
It's a massive step towards treating models as interchangeable functional components rather than just these mysterious black boxes we throw prompts at.
Well, for everyone out there listening who is managing a fleet of models or trying to build complex agentic systems, this paper definitely seems like required reading. The shift from implicit RL policy to explicit skill modeling is just too compelling to ignore.
Absolutely. I mean, it's highly efficient, it's completely interpretable, and it saves you a ton of money at runtime. That is the holy trinity for enterprise AI.
Well, that's going to do it for this deep dive. Thanks for tuning in as we explored Skill Orchestra and the future of AI routing. We'll catch you on the next one.
Thanks, everyone. Keep building.